In this lecture, we will continue our discussion on the various methods used to test seed viability. Previously, we described the germination test and the tetrazolium test, both of which are widely applied and form the foundation of seed quality assessment. The germination test provides a direct measure of a seedlot's ability to produce normal seedlings under standardized conditions, while the tetrazolium test offers a rapid biochemical method to distinguish living from dead tissues. Building on this, we will now turn to additional approaches that complement or extend these methods. Another method used to evaluate seed viability is the vital coloring method. This approach is based on the principle of differential staining, where live and dead tissues in the seed respond differently when exposed to certain dyes. Several examples of this method exist, each highlighting different aspects of seed quality. One example is the use of indoxyl acetate. This dye is particularly useful for detecting cracks and damage to the seed coat that may result from mechanical stress during harvesting or post-harvest handling. In practice, seeds are soaked in 0.1% indoxyl acetate solution for about 10 seconds and then sprayed with an ammonium solution for another 10 seconds. Lesions or damaged areas of the seed coat react to the treatment and turn a purplish-green color, making the extent of mechanical injury clearly visible. These soybean seeds were treated with indoxyl acetate. As you can see, some of them show regions that have turned purplish, which indicates damage to the seed coat. Another example is the use of fast green. This dye is employed to reveal mechanical injuries and physical fractures in seed coats. Seeds are soaked in 0.1% fast green solution for only 15 to 30 seconds. The dye penetrates any fractured areas of the seed coat and stains the embryo green, making the damage clearly visible. In these images, you can see soybean and corn seeds that have been treated with fast green. The seeds showing green staining, especially in the embryonic axis of the corn seeds, indicate the presence of mechanical damage to the seed coat. Another dye that can be used in vital coloring is ferric chloride. This chemical is particularly effective in revealing mechanical injuries and physical fractures in seed coats. Seeds are soaked in 20% ferric chloride solution for about 15 minutes. If the seed coat has been mechanically damaged, the injured areas absorb the solution and stain black, making the damage easy to identify. In this image, you can see alfalfa seeds treated with ferric chloride. The black staining clearly indicates the presence of seed coat damage caused by mechanical stress. Aside from the vital coloring methods, seed viability can also be assessed using the enzyme activity method. This approach is based on measuring the activity of specific enzymes in imbibed seeds, since enzyme function is a reliable indicator of living, metabolically active tissues. A variety of enzymes have been used for this purpose, including lipase, amylase, catalase, peroxidase, and dehydrogenase. Recall that amylase is an enzyme necessary for the breakdown of starch, while lipase, catalase, peroxidase, and dehydrogenase are involved in the breakdown of stored fats in seeds. In the images shown in this slide, we see quinoa seeds stained with diaminobenzidine. The appearance of browning indicates the presence of peroxidase activity in the tissues, as well as the presence of hydrogen peroxide. This reaction provides a clear visual marker of enzyme activity and, by extension, seed viability. The hydrogen peroxide test is based on the positive effects of hydrogen peroxide on seed germination. Hydrogen peroxide breaks down into water and oxygen, which enrich the environment around the seed and stimulates germination. To conduct the test, the seed coat is cut at the radical end, allowing a 1% hydrogen peroxide solution to permeate the interior of the seed. Rapid root protrusion is then used as a measure of seed viability. In addition, hydrogen peroxide can be visualized through staining. For example, in germinating lepidium seeds treated with TMB, the presence of hydrogen peroxide causes the tissues to turn blue, providing a clear indicator of enzymatic activity and therefore viability. So far, we've looked at vital coloring methods, enzyme activity methods, and the hydrogen peroxide test. Together, these approaches demonstrate how both structural and biochemical indicators can be used to assess seed viability. Next, we'll turn to the conductivity test, which evaluates seed vigor by measuring membrane integrity. The conductivity test is based on the principle that as seed deterioration progresses, cell membranes lose their integrity. Damaged membranes become more rigid and increasingly permeable to water. This higher permeability leads to greater leakage of cellular solutes, such as electrolytes, into the surrounding solution. The extent of this cellular leakage can be quantified by measuring the electrical conductivity of the solution where seeds have been soaked. A higher conductivity reading indicates greater leakage and therefore a lower seed quality or vigor. The graph on this slide shows the electrical conductivity of Sueda salsa seeds in both water and cadmium solution. As you can see, conductivity in both treatments increases with the time, reflecting the gradual leakage of electrolytes from the seeds as they imbibe water. However, the seeds in the cadmium solution exhibit a much higher electrical conductivity. This is because cadmium is a toxic heavy metal that disrupts normal cellular function. Specifically, cadmium damages and destabilizes cell membranes, making them more permeable. As a result, electrolytes and other solutes leak out of the cells more rapidly and in greater amounts compared to seeds soaked in pure water. The higher leakage translates directly into higher conductivity readings. In other words, the elevated conductivity in cadmium solution is an indicator of stress-induced membrane injury, showing how environmental toxins can accelerate seed deterioration and reduce vigor. The excised embryo test provides a rapid way of assessing seed viability. It is especially useful for species with dormant seeds, where traditional germination tests may take a long time. In this method, seeds are first allowed to imbibe water. The embryo is then carefully excised and placed on a moist blotter or filter paper to encourage growth. Dormant embryos will typically grow slowly, showing limited development. Embryos with extreme dormancy will fail to grow altogether. Viable, non-dormant embryos will show normal growth, providing a quick indication of seed viability. This approach significantly reduces the time required to estimate viability compared to waiting for whole seeds to overcome dormancy and germinate. Pictured here are excised embryos of eastern redbud growing in moist blotter paper. Last but not least, we have the X-ray test. The X-ray test is not a viability test per se, but it provides information that is useful in assessing seed viability. It can reveal abnormal morphology or mechanical damage that may impair germination. Take a look at some examples here. In the left panel, radiograph images of bell pepper seeds show a partially filled embryonic cavity in A and a completely filled embryonic cavity in B. In the right panel, X-ray images of fully filled bell pepper seeds display abnormalities. In picture 1, there is a crack in the cotyledon, while in picture 2, there is no differentiation in the cotyledon. In summary, seed viability in the general sense refers to the ability of seeds to germinate and produce normal seedlings. More specifically, seed viability denotes the degree to which a seed is alive and metabolically active. In this context, seeds may contain both living and dead tissues, which may or may not be capable of germination. Viability testing adds value to a seed lot by providing information that helps determine appropriate storage requirements for seeds. There are several methods for testing seed viability, with germination and tetrazolium tests being the most widely accepted. As we wrap up this course, I want to take a moment to thank you for your commitment and perseverance throughout the semester. By the end of this term, we would have gone through 36 lectures, 25 quizzes, and 8 exams, a true test of focus and endurance. Your dedication to engaging with the materials and staying the course is something I deeply appreciate. I hope the knowledge and skills you've gained here will serve you well in your future studies and beyond. Congratulations on making it through, and I wish you continued success in all that lies ahead.